We are going to talk today about analytics everywhere, an overview for operations managers. So my name is Carrie Beam, and today I'm going to be talking to you a little bit about analytics, and in particular, what is it, how do we teach it here at Arkansas, and then at the end, a little bit of why you too might want to study it a little bit here at Arkansas. I'm going to cover an introduction to analytics today. We're going to cover our analytics framework, and it breaks analytics out into three different types. There's descriptive, predictive, and prescriptive analytics. I will go into more detail about what each of these are in the presentation, but basically descriptive is telling you what you got. Predictive is making a prediction about the future. What will you get? And prescriptive is, given we know what we got, and given we've got our prediction, what should we do about it? I'll talk a little bit about the course development process here at the University of Arkansas and our courses, and then I'll take some questions. So analytics is kind of this hot new area. We knew that it was hot in 2014 when it made the cover of Time magazine, was the answers issue, and they covered all sorts of analytics questions. And from there, it was just a matter of time before this fabulous data analytics with R textbook came out. And from there was only one thing to do about it, which is to put a big red razorback on top of it and run our class here. So that's where we are. We now have a lot of data on this planet. How much is a lot? Well, according to IDC, in 2011, we created 1.8 zettabytes. That's about 1.8 trillion gigs of information. It's enough data to fill 57 billion Apple iPads. That's enough iPads to build a great iPad wall of China twice. By 2015, we were generating enough data that if you put it all on a Blu-ray disc and stacked it up as high as 4 Eiffel Towers, it would fill them all. And lest you think that analytics is all for the serious, you will be relieved to note that the dating app Tinder is reporting 1 billion daily swipes. So this means if you are curious about whether you are hot or not, now you can ask the internet. We also now have massive computing power on top of this data. And when I say massive, I mean super massive. The sad truth of it is you could take a baby with an iPhone and running a Google search, and that half a second Google search uses more computing power than the Apollo missions from NASA. And the question is, all of them? And the answer is yes, all 11 years and 17 missions. So when you take all this data and you put it together with all this computing power, that's what you get analytics. Here I'm going to define analytics as scientific analysis of this data to drive superior business decisions. And if you're in the operations management department already, you're sort of rubbing your hands together with delight because you're saying, we were all about superior business decisions before it was cool. Now we've got better data to make even better business decisions. There's operations management applications in lean manufacturing and quality, inventory management and supply chain, and a whole bunch of other places. It's not just limited to OM. There are people who do it in marketing. There are people who do it in transportation. There's a whole healthcare analytics area. But because we are the operations management department, today's talk is going to focus more on OM applications of analytics. What kinds of tools would you use if you wanted to do analytics? Well, some of them are pretty basic. We're not quite going to stick with the abacus or the handheld calculator, but you can actually do a fair amount of reasonable analytics in Microsoft Excel, especially if you use Excel 2016. And I'll put in a little side plug. We have a fantastic Excel 2016 class here at the University of Arkansas. It's OMGP 4853. And in this, we really walk you through not just how to use Excel, but how to use Excel to do hardcore computations. There's another tool by IBM called SPSS. That's a tool you have to pay for, but it's very good. There's another one out of North Carolina called SAS. It's another tool that you have to pay for. It's also very good. The great thing about SPSS and SAS is they're scripting languages, which means you can write little programs and tell it to execute a series of instructions, and it'll do it over and over again for you. And then if you don't feel so much like paying for it, there's some open source code. There's one called Python, and there's one called R, and it's literally R like the letter of the alphabet R. Both of those are free, which means you can download them to your computer today for free. And they have a lot of open source analytics libraries. Python is excellent. At Arkansas here, we are using R project. We're using RStudio and some of the statistical packages in R to do our analytics. So here's the analytics framework. We're going to talk first about descriptive analytics. And descriptive analytics are generally trying to answer the question, what happened? The methods we're going to cover are graphical displays and k-means clustering. The next area that we're going to cover is predictive analytics. This is where you're interested in trying to answer what will happen. The techniques we're going to cover here are your KNearest Neighbors, your classification tree, and regression modeling. If you've got any type of engineering or math background, maybe the regression might be the most familiar technique to you. If you don't have it, we'll teach it to you. The last category is prescriptive analytics. And this basically says, given that you know what happened, and given that you know what's going to happen, what should you do about it? And in this one, we talk a little bit about affinity analysis. All right, I'm going to talk first a little bit about descriptive and graphical displays. Descriptive and graphical displays of data are just exactly that. You're just literally trying to describe what does my data set say. You can see here on the top left, we've got a little summary statistics from Excel. This is going to give you things like your mean, your median, your mode, your kurtosis. In our class, we go a little bit beyond that. In the bottom left here, and I'm going to see, I think I've got my little hand pointer here. But the bottom left here, we learn how to, this is produced in the language R. We make little histograms here. You can see this guy here is a bimodal histogram. There's one population there, and then there's probably another population there. You can see that you can tell it's bimodal because there's a little dip in the middle. We also do scatter plots of more than one variable. Many of you are probably familiar with that y versus x scatter plot. Here's one where we've got three variables, variable 1, 2, and 3 down the left, and the same variables, 1, 2, 3 across the bottom. Now, this diagonal part here is going to be variable 1 versus variable 1. That's not terribly interesting or exciting, so it doesn't bother to plot it. This one here is going to be variable 2 and variable 1. And you can see this tells you at a glance there's something going on here. As variable 1 is going up, variable 2 is going down. This guy down here is variable 3 and variable 1. And you can also tell at a glance here that not much of anything is happening here. So if you've got a large data set, let's say you have 10 or 20 different variables and you just want to see at a glance what's happening, you can run this kind of pairs plot in R and it'll show you. Another type of a descriptive display is a box plot. You guys have probably seen box plots before. In our class, we also talk about how to sort them out by category. A box plot will give you a little line across the middle to show you the median, which is the 50th percentile. And the top and bottom of the boxes give you the 25th and 75th percentiles. And then if you've got more stuff out to the 5th and 95th, you get these little flat things. And then if you've got people just completely beyond the pale of your data set, like this guy up here, that's an outlier. So you can see, again, box plots are a quick, easy way to quickly describe your data set. In our class, we have, it's one of my total favorite case studies, it's the Hogg Mobile case study. We have an automotive data set from the 1970s. And the case study says the Hogg Mobile is a new retro automobile, and it gets 40 miles to the gallon. It's got 4 cylinders, 150 cc's of displacement, and 175 horsepower. Can you visualize this? Can we determine if this is going to be competitive in the retro market? This is a job for descriptive statistics. We can run some descriptive statistics on our data set, and this little red thing shows where the Hogg Mobile is. So you can see at a glance that of the fuel efficiency, it's actually pretty competitive. But over here for the engine displacement, not so much. You can also see over here where the number of cylinders over here, and I think this is probably miles per gallon on the bottom. You can see our Hogg Mobile is, for the number of cylinders he's got, he's actually getting pretty good gas mileage. And then down here again, this is a box plot. You can see the engine displacement, and there is our fabulous Hogg Mobile. If you do manage to stick around till the end of the presentation, we have a visual on the Hogg Mobile for you. It's a super treat. Another descriptive method is called k-means clustering. And k is just a stand-in for some integer. So you could do 2 means, 3 means, 4 means, 5 means, whatever. This is what you use when you want to group multidimensional data along 2 or more dimensions. The idea here is you want to minimize your within cluster variance. So everybody in the same cluster is going to be very similar to each other, and maximize your between cluster variance. So different clusters are going to be very different from each other. It's best when your axes are numeric, and this does require you to scale your data. This is just an example of what it might look like. Here's your data here, these little blue dots, or each little blue dot is a data point. You could say, well, everybody's all in one big happy family here. This is too few clusters, this is one. You could also say, every man is an island, and pretty much draw a whole bunch of clusters. This is probably too many clusters. Like this little thing down here probably doesn't need to be its own cluster. And so you think, gosh, this is 3 clustering down here. This is just right. We've got everybody in their area with each other, but they're also, the midpoints of each of these clusters are pretty far apart from each other. So the question with the algorithm here is, how many clusters do you need to give yourself the best representation of your data? In our class, we've got a background data set. It contains United States demographic information from 1977 because disco lives forever. It contains population, income, illiteracy, life expectancy, murder rates, high school graduation rates, even frost data, and area information for each of the 50 United States in 1977. And the sample question is, can you find the 2 best variables to do the clustering on, and then find the optimal number of clusters to describe this? This is an example of a homework turned in by 2 of our STAR students, Eddie Robinson and Scott Smith. They're also on our faculty here, so we are delighted that they're our STAR students. You can see down here on the bottom, let me see. I totally can't read that slide, but over here you can see you've got the murder rate and the life expectancy, and you can see as the life expectancy goes up here, the murder rate is going down. And then they colored it by their clusters. So they said these states up here are one cluster, these green ones are another cluster, these guys are a 3rd cluster, and a 4th cluster. And you could play with this and you can work with your data set. Other students did things like illiteracy versus income or high school graduation rates. There wasn't a lot of clustering to be had with high school graduation rates versus frost data, but you get the picture. So we've talked about descriptive analytics here. We've talked a little bit about how to figure out what happened. We're now going to look into predictive analytics, which are techniques to predict what is going to happen. The next algorithm we cover is something called KNearest Neighbors. And again, the K just stands for a number. So when you're finalized with this, it's going to be like the 3 nearest neighbors or your 5 nearest neighbors. What you want to do is you want to classify outcomes. Typically, your data set will have some outcome like they bought something or they didn't buy something. Or in our case, this is a machine reliability thing. So the machine either melted down or it didn't melt down. So you've got a target variable, and that's the thing you want to predict. You have a training data set for which the outcomes are known. And then you have a prediction point where you want to predict it. In our case, we've got temperature across the bottom here for our machine. How hot did it get? And the duration of how long it ran. And you can see all of these things with green are when it did not melt down. So here it actually was pretty warm and didn't run for very long and did not melt down. And then these orange boxes are where it did melt down. So you could see as it got to be too warm, even at short durations, it melted. And we want to predict Mr. Question Mark here. Do we think, is he going to melt or is he not going to melt if it's this hot out and we want to run it for this duration? Well, if we were to use a 3 nearest neighbors algorithm, what we do is we say, here's our data point of interest. Let's look at his 3 nearest neighbors. Well, the 3 data points closest to him are probably 1, 2, 3. So of these 3 nearest guys, 2 of them are orange, 1 of them is green. So we just take a vote of the 3 nearest neighbors. They're voting for orange. So in that case, we predict he's also going to be orange, which is a meltdown. So we say, if you're going to run your machine under these conditions, this temperature and this duration, we think it's going to melt. If we had run a 5 nearest neighbors, what we would do is we would take the 5 nearest data points, which in this case are probably 1, 2, 3, 4, and maybe that guy 5. And in that case, the vote is now 3-2 in favor of green. So if you had run a 5 nearest neighbors algorithm on this, what you would say is, you know what, we think you're probably not going to melt down. We think you're probably going to be okay. In the class, we go over how to choose whether it's 3, 5, 7, 9, or other numbers. The idea is you want to get the smallest number there that still gives you really good results, because the bigger numbers give you more computational complexity. In our class, the students did KNearest Neighbors on a data set that included family income and family size, and the target variable was whether they bought or did not buy a vacation package. And our sample question is, will a new prospect, so this is our question mark, with an income of $89,000 and a family size of 3, will they buy or will they not buy? And then the next question is, how much better is this model than chance alone? Well, we ran the KNearest Neighbors on it, and this is our classification matrix. You can see this is where people actually were buyers. We had 22 who were buyers who were predicted to be buyers. We had another 12 who actually were buyers, but they were mistakenly predicted to be non-buyers. Then you could see down here, these guys, these 15 were also mistakenly classified. And then these 51 down here were correctly classified. So how many did it get right? Well, it got 22 of the buyers right, plus 51 of the non-buyers right. So that's 73 out of 100. So 73% about these guys are done correctly. If we didn't have a model, we would just have to go with chance alone. And we would say, well, you know, 66% of this data set is not a buyer. So I'm just going to guess everybody's not a buyer. It's kind of a pessimistic way to go through life, but we would say about 2/3. So in this case, our model's doing better. We can classify 73% correctly, whereas chance alone would just say 66%. So this model's lift is about 73 over 66, or about 1.11. So you say it's about 11% better than chance alone. So if this were in the real world, people would be ecstatic. Any kind of lift above about 5% is considered very good for a model. The next technique I'm going to talk about is something called classification trees. Again, you're trying to do the same kind of thing you were trying to do with the KNearest Neighbors, where you're trying to classify outcomes. A cool thing about these is they do really well with nonlinear data. We use the R-part algorithm, recursive partitioning algorithm. It starts at a root node, and what it does is it goes through all of the possible factors, and it says, can I split, if I split my data on this factor, will it split into 2 very different groups or not? And it picks the one that gives it the biggest split on the best, most differential split. And then it goes over and it says, okay, now I've split it. We'll go back and keep running it. And it keeps splitting itself into different branches until it can't split anymore. Sometimes it makes an enormous tree, a glorious tree. And in that case, you need to prune the tree, because a tree with 2,000 nodes is going to be unwieldy. You can't really manage that. You can prune it using a minimum leaf size or a minimum size node to split. And this is all stuff we cover in our class. So here's just an example of a classification tree here. And this is all data that I generated for this particular assignment. But I'm hopeful that it's actually somewhat true in the real world, because it has people with good grades getting better job offers. So we say, given data about student GPA, major, and school, and whether they were hired or not, can we outline some decision rules here? And a sample question would be, if I have a certain GPA and a certain major, what are my chances of getting hired? This is the kind of tree that the software builds. You can see this root node is everybody here. It's 100% of our data. And then it says, remember how I talked about how it was going through the variables to see what gave you the best split? For this data, the best split was on GPA. And in particular, it was like whether your GPA was or was not above a 3.0. If it was above a 3.0, that's a yes, you go to the left. So everybody over here, this is about 50% of everybody, has a GPA of above 3.0. And these are your folks who have a GPA of not above 3.0. And then there's a different split down here. Of the good students, of the GPAs above 3.0, the next most important factor was what your major was. And it's saying if your major is business, computers, or OMGT, you get to go down into this leaf down here. And if your major was anything else, you get to go down over here. So if you look down here, this is about 38% of the pool, but these folks down here are having a 93% chance of being hired. So let's see. So we've got our sample question. I've got a GPA between 2.2 and 3.0 and an OMGT major. Want to know what this model would say my chances of getting hired are? Well, we start out here. Your GPA is less than 3.0, so you go down here. And then this split here is on major, so the OMGT major, so it goes down here. And then there's one more split down here on GPA, and this one says the GPA is better than 2.2 or not, and yours is. So in this case, you're going to end up down here in the green box with 20% of the pool, and this is going to give you about a 75% chance of getting hired, or more specifically, about 75% of the people in this bucket got hired. One of the cool things about this is it's nonlinear. You can see it'll split it at 2.2 or 3.0. It doesn't necessarily assume that 3 is twice as good as 1.5. And another nice thing about these kinds of models is you could see here the secondary split was on grade point average, and here the secondary split was on school. So the tree does not need to be symmetric. It has a lot of freedom to really mold to the data. These guys are vulnerable to overfitting, and you have to be careful about that. But this is a good example of the classification trees we run. The next technique we cover is linear regression. And if I were giving this seminar live right about now, I would be seeing all these happy smiles on people's faces because you're familiar with this. You want to predict scale, numeric outcomes. Regression is really good at linear things. So for example, if this variable down here goes up, and this other one goes up in a total straight line, that's great. It's also pretty good at logistic or other predictable curves. Like this, for example, could be lifetime incidence of lung cancer with the amount that you smoke. So if you never smoke, you have a very low probability of lung cancer. There's some amount of smoking, which gives you sort of a 50-50 chance. And then there's some higher amount that really puts you into a very high category there. Regression is bad at discontinuous data. And discontinuous data, the best example I know of is age and fast food. When you're young, you really like those Happy Meals, so you eat a lot of it. When you're medium-sized and have no kids of your own, you may have gotten bit by the health food bug and you're now shopping at Whole Foods, and or you're just able to upgrade and you're able to go out to places that are not McDonald's. And then you get to this age and you have kids again and you are right back in with those Happy Meals. And then your kids grow up and you say, I am never having another Happy Meal again. So this is a very predictable lifestyle pattern, but you can't really draw a straight line or even fit a curve to it nicely. So this kind of data pattern is something for which regression really is not a good fit. So in our class, we run simple and multiple linear regression. You're always just trying to predict one output variable. With simple linear regression, you're using one input, one x, to predict one y. With multiple linear regression, you're using a bunch of x's to predict one y. Some sample questions here. We had EPA data, groundwater runoff data in Bishop, California, which is kind of outside of Los Angeles. We're using previous year's groundwater runoff data from 6 different locations to predict this year's runoff in Bishop, California. The question is, do you need to bring in some flood control measures? As you can see, over here is a regression data set. Here's your x variable down here. Here's your y. This is what you're predicting. And this blue line here is your regression line. And so this red point here, if this is where you are, you want to predict it, well, you go up here to the blue line and then go over. So our regression line would predict that the red dot should actually be probably about here. So he's actually a little higher than predicted. Here's a little bit of the sample R code that people run. I'm including this in here just to show you how few lines of computer code you need to make this thing run this big regression. Here's one where we say model 2, and this left arrow means assign the value to. LM is linear model, so regression, and we're telling it weight is what we want to predict, and we want to see if height, shoe size, IQ, and how much weight you lift at the gym each week, and how many hours you watch TV, if any of those are going to be good predictors of what your weight is. And then you can also see you can print out your model here. The last bit here is I'm headed into the prescriptive part of the analysis. This is given that we know what we know, what should we do about it? The type of analysis we do in this class is called affinity analysis. It's also sometimes called market basket analysis. You have probably been subject to this if you've ever bought anything at Amazon. If you go buy something there on Monday, you buy a book about tennis. And then Tuesday you log back in and it says, people who bought that book also like these other 3 books, and they'll show you a couple of other books that are similar to the one you bought. It's this kind of algorithm that they're running to do that. The algorithm is unsupervised, and what that means is there's no necessarily right answer like there would be with regression or with, we predict whether he's going to buy this or not. Instead, we're just going to say, people who like this also often like that. If you're familiar with probability theory, you could say, let's look at our grocery basket here. And we want to know what is the probability somebody's going to buy cheese given that they already have cherry and bacon in the cart. In our affinity analysis speak, the way this is written is cherry and bacon as your predecessors, and then to see if the rule says the successor is going to be cheese. These guys are called the antecedents, and these guys are called the consequence. There's measures of affinity, which is measures of how much certain things like to be in the cart together. We use measures of confidence, measures of support, and measures of lift. In our class, we cover them a more full definition of each of these guys, but support is basically how frequently does this thing happen? If it only happens once in 1,000 carts, it might not be worth putting a lot of attention into. The confidence is what percentage of all transactions with this antecedent also have this consequence. It's another way to measure sort of how much does this happen. And the last one is the lift. And the lift is sort of the big Mac Daddy of all of these. The lift is how much more frequently does this happen than by chance alone. So for example, let's say you have a rule that says if they've got cherry, cabbage, and bacon in their cart, they're also going to have cheese in their cart. If the lift of this is 1.0, that tells you that there's no predictive value here at all. They are just as likely to put cheese in the cart whether they do or don't have cherry, cabbage, and bacon. If your lift is down here is 0.7, like if they have cherry, cabbage, and bacon, and then the lift on the bread prediction is only 0.7, that says they're 30% less likely to have bread. So that says they are not buying bread with these other ingredients for whatever reason. And you've probably figured it out by now, but this lift of 1.8 for your cherry, cabbage, and bacon predicting jam, this gets a gold star. The reason it gets a gold star is because the lift here is 1.8. So it says people are 1.8 times more likely to buy jam that when they've got these other things in the cart than they would be just to put jam in an empty cart or into a cart with other stuff in it. Our students learn the underlying math of affinity analysis, and they build a recommender system for paint colors, camping equipment, and other applications. A sample question here would be you've been given a lot of data from a paint store about what colors of paint people had in their shopping carts when they checked out. And it said, you've learned that a customer put a gallon of Utah Sky paint in the shopping cart. And for those of you who don't know this, Utah Sky is blue, so it's a beautiful bright blue paint color. What additional colors would you suggest for this customer? And you can see this is a little bit of the printout of the kind of things that you get here. Our very top thing here has blue, Utah Sky, and white in it. And you can see that then it's suggesting on the right-hand side a color called Kasbah, which is kind of like a Moroccan dusty orange. And if you look at that, the lift on that is 40. And what that is telling you is that if people have these 3 colors in their cart, they're 40 times more likely to also put this color in their cart. So you could certainly look through your rules to find only Utah Sky all by itself over here, but you could also say, Utah Sky is in the cart here, here, and let's see, both of those times it's predicting Kasbah with pretty high lift. So I think the Kasbah is what we're going to suggest to these people. This is exactly what Amazon is doing. This is probably a little bit tricked out, but this is pretty much exactly what Amazon is doing when it recommends that other book to you. So the next question is everybody says, gosh, you just told me all these way cool things you can do with analytics, and you also told me that I could do them for free with this programming language called R. What does R Studio look like? Well, here's what it looks like. It's just a screenshot. We run this, you can download this to your own computer, or you could run it for free in our virtual lab. You get a little screenshot here. And up here is the top area where you get to type your code. Here's an example of the code. Down here on the bottom is where you get to run the code. So you actually get to press enter down here and it'll execute your code. And then you've got a little history of what we did up here. And then you've got up some more talking here. So you can see it's a programming environment. It's definitely not a graphical user interface in that it's not like an iPhone where there's only one button to push, but it's not awful in terms of programming. We're not asking you to write assembly code in hexadecimal here. So let's talk a little bit about our analytics class. It's OMGT 5653. It's also called 577V, and the two things have exactly identical content. It's just a matter of what you register for. We have a couple components to it. We have language. We have a virtual lab that you can log into. The way you log into this is you just open up a browser on your computer screen, and then inside that browser, it goes to the virtual lab where it lets you run R. You do need some kind of computer. And then the last thing we need, of course, is a curious student. Each week, an analytics technique is introduced. We have videos on how to do it. A lot of them, you get to watch me writing a sample program. I've recorded screenshots of myself doing that. We give you scripts to run. And then the textbook is really good. It shows you examples. And so when you start, you get to first watch me do it. Then you get to try doing it in the textbook on your own. And then you have to really start to do it. We have automatically graded quizzes which test individual comprehension. This gives you immediate feedback, so you'll know right away if you're doing it right or not. And then each week you'll have a group project which requires larger synthesis and writing skills. Each group project has an executive summary, and we really work hard on helping people craft good executive summaries. One of our big program objectives here is to communicate results to senior stakeholders and decision makers. In this class, you'll get a lot of exhaustive practice in writing a good executive summary so that if the senior decision maker only read your executive summary, they would still know what to do. There's also a midterm and a final exam. Those are done on your own, and they test your comprehension of the material. So there's applications to operations management. I hinted at this a little bit at the beginning of the talk, but I'll go over some more details here. If you've got descriptive analytics, descriptive statistics, they can pretty much go to any of the 10 OM decisions, but one place you might be especially interested in putting them is in a quality management course. They're taking tons of data about control charts and defects. You could also be very interested in human resources with job design, trying to visualize or describe what exactly are people doing all day long, what's the workflow. Also with design of goods and services, what should something look like? What kinds of things are people saying? If you have a customer service or a customer satisfaction survey, sometimes descriptive statistics are really helpful. You can get a box plot of customer answers to certain questions, and you can split it by different categories, like by gender or by whether someone's a member of your loyalty program or not. If you wanted to do the K-means clustering, that is great for location strategies, and it's also got some applications to maintenance and reliability, like we saw in our example about whether your machine is going to melt or not. The predictive analytics, we've got the KNearest Neighbors, that is a forecasting technique. Now, many of you who've come through our Intro to Operations Management class are all about moving averages and exponential smoothing for forecasting time series. Just be aware there are other things you can forecast, and this is a different way to forecast some things. There's classification trees. Again, those are very helpful in quality. Just like in our example with our school kids about who got hired and who didn't get hired, you could dump a whole bunch of manufacturing data in there and ask it to build you a tree to try to predict whether something would or would not have a defect. And you could see if a particular shift or a particular operator, particular supplier, or any other data factor that you take might have an impact on that. For regression, again, it's another forecasting technique. The regression, if you're going to use it for forecasting, it's often used in a time series context, but it doesn't always have to be done that way. And then the prescriptive analytics or affinity analysis. This can be done with design of goods and services. So for example, you could take your little widget and note all the different options on it and see who buys what kind of widget. Do they buy the one with bells on it? Do they buy the red one? Do they buy the one that spins around? And dump that into an affinity analysis algorithm, and it will tell you people who buy the one with bells on it also want it to be red. Same idea with quality. You can look at, try to figure out what is the voice of the customer, what is the fitness for use here. So a little summary of the talk to date. We've given you an introduction to our analytics here. We've covered our analytics framework of descriptive, predictive, and prescriptive analytics. Talked a little bit about the course here at the U of A. And it says I'll take questions now. I'm actually going to cover 3 more slides and then I will totally take questions. But I do want to point out to you, we have the most glorious graphic, the second most glorious graphic ever here. We've got our Razorback taking off on rocket fuel on our data book. This is the most glorious graphic ever. This is the Hogg Mobile. And so if you can think of no other reason you want to take the analytics class, you probably want to take it because when else are you going to be able to have a team project in which you are in all seriousness turning in something with this on the cover? All right, so now I've piqued a little bit of interest. I just want to go over a few final things here with our online master's programs. We've got 3 online master's programs here available to you all. And the key here is they are exactly what they say. They are totally online. You can do every one of these from the comfort of your own couch, and they are all master's degrees. The first one over here is our MS in Engineering. The second one is MS in Engineering Management. And you guys are smart, so you'll notice you got to listen for the second word here. And the third one is the MS in Operations Management. You guys are smart, you have to look for the first word here. All of them have comprehensive exams. If you are going to look at the MS in Engineering, you get to take 3 electives chosen from a whole bunch of courses. In the Engineering Management, you also get 3 electives. The MS in OM, you get a little bit more wiggle room here. You get 6 electives chosen from our OMGT and our MSEM courses. If you're doing your Master's in Engineering, you've got 4 core courses from this like super geek list over here. If you're doing it in Engineering Management, you've got 4 core courses, which are listed right here. And then if you're doing it in OM, you have our intro class, our finance, our strategic management, and our project management. And then you get to take a few more classes. You just need, for the MS in Engineering, you need 3-course engineering sequence to form a cohesive topic area. And we're a big school, and we have a lot of stuff to offer. So I'm totally sure you'll find something that fascinates you. Same thing over here. And then to get your MS in OM, you need to satisfy your undergrad prerequisites and a whole bunch of other little courses down here. Now, you are all falling off the edge of your couches. You are saying, how can I get a piece of this? What do I need to come here? Well, if you want to do any of these first 2 programs, you need an ABET accredited bachelor's degree in engineering. And you'll know it if you have it because your diploma will have the word engineering on it. If you don't have an undergraduate degree in engineering, but you do have a regionally accredited bachelor's degree, the MSOM program is the program for you. So the MS in Operations Management, at a glance, we've got online and live course options. We've got a couple prerequisite courses. It's 30 credit hours. There's 5 8-week sessions per year and 5 enrollment periods. They go August, October, January, March, and May. So pretty much whenever you're ready, we are here for you. The tuition is $289 per credit hour, and there's no out-of-state tuition surcharge. So wherever you are, it's $289 per credit hour. You can complete the entire degree for an investment of about $11,000 to $15,000, depending on how many prereqs you need. And if you did well in your undergrad, if you did a 3.0 bachelor's or better, there's no GRE or GMAT required. You don't have to write a thesis. You do have to take your oral comprehensive exams, but the good news is people typically do very well on them when they've prepared through the program. It can be completed as fast as 1 year, but if life is getting in the way, you have up to 6 years to complete our MSOM program. There's a project management graduate certificate at a glance as well. Same thing, online live course options. It's 12 credit hours. Again, we roll all around the calendar, so whenever you want this, we are here for you. The tuition is the same. The GPA is a 2.5 GPA with the bachelor's degree required. And their certificate courses can also count towards the MSOM degree. So if you think you want to do both of these guys, talk to your advisor early on so you can get the right level of classes lined up for yourself. And I think that concludes the talk. It has been an absolute pleasure to have you all here with me today. And next time you walk around in the world and you see some computer recommending something to you, you can think to yourself, I know the kind of analytics algorithm they're running.